Hello again. Let's talk about accuracy, precision, and error. And we're continuing with our discussion on making measurements. So, when you make a measurement, how do you know how good it is? Well, you look at the accuracy and you look at precision. In science, accuracy tells you how close your measurement comes to the real value, the true value, the correct value. I like alliteration. A for accuracy, A actually accepted answer. It's the right answer. We always hope to be right. In this class, we'll be comparing our measurements to known values, but when you're doing research, you don't always know what the actual accepted answer is. But if you do enough repetitions, eventually you can have confidence that it's probably whatever it comes out to be. It varies from experiment to experiment, of course. Precision, on the other hand, is, in a scientific definition, how close all your measurements are to each other. Are they consistent? Are they repeatable? Do you get the same thing over and over and over again? In statistics, we look at the range. What's the low? What's the high? How close together are they? That's related to precision. Now, if you're accurate and if you're precise, you have a device that's marked with a lot of lines, you're more likely to get the right result. Okay, so we use these two terms kind of interchangeably in everyday language. Scientists make, kind of split hairs and make a distinction between them. If you have a precisely marked, with lots of lines, if you will, instrument, you're more likely to have repeated measurements, and you're also, hopefully, more likely to be right. Okay? Again, our goal is to be right all the time, right? That's our goal in science and in life. We want to be correct, and we want to be correct all the time. Okay? Accurate and precise. We want both. We evaluate how accurate a measurement is by comparing it to some known value. If there is one, there isn't always one, but in this class there will be. And if we're evaluating the precision, we want to have repeated results that come out the same. So when we get to measuring the thickness of our aluminum foil, we're going to have data from 2 pieces of foil. In reality, you need hundreds, but we can't take the time for that. The book uses an example of playing darts to try and demonstrate accuracy and precision. You know, the goal of good darts probably is to hit that center red dot in the dartboard. And this is obviously not me playing darts. All the darts on this one are really, really close to the center. I can't really tell if they're in there or not, but they're very accurate. They're close, close, close. And they're all close together. Okay? They're repeated over and over again. So that's good accuracy and precision. This is actually the hardest for statisticians to figure out. So one of the things you do when you collect data is you run it through some analysis. If you get the same thing over and over and over and over again, you have more confidence that that might be the right answer. Unfortunately, this one is, these 3 darts are way far away. Well, they're not on the wall, but they're far away from the correct spot, the red dot in the middle. So you have false confidence in these, if you will, if these are measurements, because there's good precision, but they're not hitting the target, so that's bad accuracy. This one's closer to how I play, all over the place, none of them at the target, and none of them close together. Poor accuracy, poor precision, not good. That's easy. Usually you can tell pretty quickly. If they're all over, if the data's all over the place, you can have, you don't have any confidence in it. Accepted determining error is the next thing that we do. So if there is a known accepted value, you compare your experimental values to that. Of course, hopefully they're the same, but they might be off a little bit. And so we determine something called error. You take your experimental value, which you got in the laboratory, and you subtract from it the accepted value. Now, it doesn't take a rocket scientist to figure out that sometimes your experimental value is going to be high and sometimes it's low. If it's higher than accepted, you're going to get a positive error. If it's lower than the accepted is bigger, you'll get a negative value. So you've probably seen this on like political polls, plus or minus. Okay, there's a range. And that's okay. When you make a measurement, you might be a little smaller than it should be. It might be a little bigger than it should be. It happens. The percent error is super easy to calculate. It's just like all percentages. It's the absolute value of the error, so we don't worry about plus or minus. And the whole, the total, the correct accepted value goes in the denominator. And then you just multiply by 100 like you do in normal percent calculations. We always expect a little bit of error in the laboratory. If you're within 2% of the accepted value, that's considered spot on, perfect. Um, no deduction of points. In college, however, if you get 5% error, you could be 5% low, you could be 5% high. That's a 10% range. That's a pretty big range. They'll probably take off some points. And if you get past 10% error, 10% low, 10% high, that's a 20% range. They'll probably dock you pretty hard, but I'm not going to do that in here. Okay. An example for you to see the whole process. You're boiling water, your thermometer says 99.1. You know the accepted value to boil water with 1 atmosphere of pressure is 100 degrees Celsius. So you subtract that, obviously you would see that that would give you a negative 0.9, but because it's absolute, right, from math, we just do 0.9 divided by the accepted value, which is 100, times 100%. So this ends up with a very small percent error, less than 1% error. That's acceptable. Okay, so don't let it bother you if your thermometers when we're doing stuff read 99. It's okay. It's not that big of a deal. All right, and you've probably seen a bathroom scale like this has a little knob on the side where you can adjust so that the line lines up with 0, and then when you step on it, you get whatever you should have. So this, if you're stepping on this, there's going to be automatically, what is that, like 8 pounds error on this one. That's a pretty tiny person, but at any rate, you have to make sure that your balances are 0. We'll be using electronic balances when we get to campus, and they have a little tare or 0 button on them. You want to make sure that you always press that before you get on, and make sure it's adjusted before you do any measurements. And that's it for now. We'll pick up on this stuff